Great, thank you very much. Okay, without further ado, a couple of points. In general, very happy for people to interrupt me if they want to interrupt me. And this is my first time lecturing this material, so if anyone has ideas or suggestions, feel free. But okay, phase transitions. We're all familiar with phase transitions. The most familiar one is water. But let me give a couple of examples. I'm going to write down the phase diagram, and this is going to be the beginning of our understanding of phase transitions, is to be able to write down a phase diagram. So I'm going to pick the example of helium-4. And let's write down the phase diagram for this. In pressure versus temperature. And at low pressure and high enough temperature, we know that helium-4 is in a gas phase. And as we decrease the temperature, at some point, we have a phase transition, and here we have a first order phase transition from a gas phase to a liquid phase. This happens at some temperature, I think it's roughly 2 degrees Kelvin, which is, roughly speaking, some kind of interaction energy divided by the Boltzmann constant. After this plot, I will obviously set Boltzmann's constant to 1. The phase diagram is a bit more complicated than this. You may well know that at low enough temperatures, there's a superfluid state, and at high enough pressures and low enough temperatures, there's a solid state. In fact, there are 2 solid states. There's one with a hexagonal crystal lattice and another with a square crystal lattice. So this is, roughly speaking, what the phase diagram of helium-4 looks like. I just realized I don't have a clock to look at, so I'm just going to get one out. This dashed line here is a line of second order phase transitions. And the full lines are lines of first order phase transitions. That is, if we change the temperature and we change the pressure to go across one of these lines, that's what happens. And this line of first order phase transitions ends in an endpoint. The endpoint itself, sometimes called the critical point, is second order. But the line is a line of first order transitions. Okay, that's helium-4. I thought I'd show it because it has quite a lot of stuff going on. In general, if we pick an interesting model, there'll be quite a lot of stuff going on. Let's pick another interesting model of more interest to people here. Let's pick QCD. And here I'm going to kind of slightly switch things so that I have the temperature on the y-axis, just because this is the conventional way of drawing things, and the chemical potential on the x-axis. And if at very low temperatures, or temperatures that we know, we have hadrons. And at low pressures. And if you get to high enough temperatures, you get a quark-gluon plasma. If instead of going up in temperature, we go across and basically increase the chemical potential, which is equivalent to increasing the pressure, we get a line of first order phase transitions where we get nuclear matter on the right-hand side where this is like a big neutron, or if you have a high enough chemical potential, high enough pressure, there's no space around the neutrons. You just, instead of getting separate hadrons, you just get one big blob of nuclear matter. And then let me draw some other stuff in here, which is more at very high chemical potentials, there is a color flavor locked quark superconducting phase. In between, it's expected that there's another line of first order phase transitions. There's some kind of quark fluid phase, but in general, this is not well known. On old maps, they used to write here be dragons because we don't understand this area. So this is well understood because it's under control perturbatively in QCD. This is well understood, partly because we know it from experiments, but also it's understood in terms of chiral perturbation theory. Up here is well understood because you can put it on a lattice, but over here, the lattice has a sign problem and the coupling is large, so we don't know the phase diagram. Okay, so here are a couple of phase diagrams. Let me just put some scales on here. Here we have roughly 300 MeV somewhere here, and here roughly 150 MeV. Whether these are lines of first or second order phase transitions is, what I've drawn is the current understanding, but it's not completely known. And these energy scales here are just the energy scales in your model. Yeah? Color flavor locked quark superconductor. So color flavor locked is at high chemical potentials, the masses of the up and the down and the strange quarks are small compared to mu, so they can be treated as massless. And then you have your flavor symmetry is then SU3, and like rotating amongst those three quarks, and then you also have SU3 of color symmetry, and those two get locked in sync, and this is the lowest energy state at high enough chemical potentials. And you know this because at high enough chemical potentials, the coupling goes to 0. So you can work perturbatively. Yeah, and in the middle, there could be loads of phases. We don't really understand this. So what I'm going to talk about is cosmological history, where, as you've learned in your other lectures, we start at some very high temperature and the universe cools down. That's the general picture. So on here, we'd be going from right to left. On here, we'd be going from top to bottom. And we're not just looking at QCD. We're not just looking at helium-4. We're going to be looking at models in general, whether they're the standard model or beyond the standard model, and how we can understand possible phase transitions and the phase diagram of these models. Okay. So actually, let me replace this word with determine. So what I'm going to be doing in the next few lectures is, or in fact today, yeah, and tomorrow, is someone gives you a QFT, you're interested in a QFT for whatever reason. What is the phase diagram? How do we determine this? And the first place to start is to think about order parameters. Now I'm going to give a loose definition, which is the definition that I want to use. Order parameters are observables which reveal the phase. Sometimes in the Landau theory of second-order phase transitions, order parameters used in a more specific way. I don't want to use it in that way. I want to use it in a more general way as any kind of observable which can reveal the phase. And let's give some examples. I'm going to start with a familiar one, global symmetry breaking, where the order parameter really is the order parameter that we have in the Landau theory. And let's write a potential for some field phi, which looks like -1/2 mu squared phi a plus quarter lambda phi a squared. And a is 1, 2 to n. So this potential, let's say we have a model, a QFT. With this potential has an O-N symmetry. Now, as you know, it may be that the state has a lower symmetry than the potential. For example, the state can break this. If, for example, the state looks like some value times delta A1. So it's just in the first direction. You can think of this as just being an n-dimensional vector. It has something in the first direction. What symmetry does that break? It breaks symmetries that rotate the first direction, but it doesn't break symmetries that rotate 2 to n. You can rotate 2 to n. Fine. So this breaks us down to O(n minus 1). Then this, in that case, would be our observable, which tells us which phase we're in. How about the Higgs mechanism? So in gauge-fixed perturbation theory, which is how we normally learn the Higgs mechanism, we learn the same story here. And in gauge-fixed perturbation theory, the story is pretty much the same. At weak enough coupling, we have what looks like a global symmetry breaking. But there's an issue that, if I go to the bottom, can people see? Yeah, okay. Let's try to go right to the bottom. So this thing in a gauge theory is gauge dependent. And as a consequence, there is something called the Litz's theorem, which tells us that because it's gauge dependent, it's 0. All gauge dependent expectation values are 0, which means gauge symmetry is never broken. Let's not go right to the bottom, I'll continue over here. Instead, if we want some gauge invariant order parameter, we can look at something like this. But this thing is rather different to just phi in the global symmetry case, because this thing is never 0. This is okay, it's positive definite up to renormalization, but this 0 is not a special point of this. 0 is a special point of this, but not a special point of this. So there's no symmetry breaking, but this can still tell us what phase we're in. Yeah, we'll go more into detail into the Higgs mechanism later. Another example, chiral symmetry breaking. We can break symmetries that are related to space-time symmetries, in some sense. So in QCD, with NF massless quarks, there's a symmetry which is SU NF left times SU NF right. That is, you can rotate the left-handed quarks and the right-handed quarks independently under this flavor symmetry group. You have two copies of the flavor symmetry group, one for the left-handed quarks and one for the right-handed quarks. But this can be spontaneously broken by something like this: quark left, quark right, plus right left. If this is non-zero, then we break the symmetry down to the diagonal subgroup. Most of these have chatted about symmetry before. How about confinement? Here we have a deconfined phase, here we have a confined phase. What kind of an order parameter can we get to determine whether or not we have confinement? If we take some big loop in space, let's call it C, big curve, and we define the path-ordered exponential of A dot ds along the curve, then the expectation value of this thing tells us which phase we're in. Are we in a confining phase or a deconfined phase? The way to think about this, if we're in a deconfined phase, and I take this curve to be extremely large, the expectation value of this operator should decompose into somehow something local which follows this path. One way to think about what is this operator, if you have a quark and an anti-quark and you create them, they have different gauge transformations at different points. So if I create this object here is the moving operator that is the thing that fixes the phase. So for a quark, so if I create a quark-antiquark pair here and annihilate them there, I will need this phase factor and to some overall possible phase factors to ensure gauge invariance, essentially. So this is part of what turns up in the expectation value of the amplitude for the probability of creating a quark-antiquark pair here and then them annihilating again here. So this is ignoring the fermion part. This is the gauge part of this amplitude. So if I average this over the gauge bits at least, this tells us the gauge contribution to this amplitude of creating a quark-antiquark pair here and annihilating them there. If the quarks can live separately and we're deconfined, then we would expect this to go like e to the minus some constant times the length of this contour. That's because I can take the contour very far apart, and it should only care about stuff that's local to the contour, because interactions are not global. In a deconfined phase, we can take the quarks far apart. But in a confined phase, there's essentially a potential which linearly rises between two quarks. So the gauge energy of two very far quarks grows with the length of the gap between them. And as a consequence, we would expect that we get e to the minus constant times the area of the curve in the confined case. And then deconfined at the top here. So if you calculate this operator and work out how it scales for large curves, you should be able to work out if you're in a confined or a deconfined phase, depending on this operator. Okay. Yeah.
Is there a relationship between the condensate that's breaking parallel symmetry breaking and the fact that we see confinement?
I don't think so. We can get this. We can do this whole confinement story without quarks, just gluons. Yeah. Some other ones, I'm not going to write down some more, but we could have, for example, just the masses of your theory. The masses of your theory might be different. The mass spectrum might be different in two different phases. Right. Now my plan is, going forward, that we will study a model, the abelian Higgs model. So one of these cases where we have a Higgs mechanism, and we'll actually do some computations and we'll actually work out what the phase diagram is. And this took some decades. So there's some decades of history of different people doing calculations and trying to understand this, and hopefully we'll go over that in 1 or 2 lectures, and hopefully understand kind of the trajectory of thought. So I've apparently been too slow at the beginning, chatting about order parameters. I'm going to use what I believe are the same conventions as Micheliner. I'm going to work in Euclidean signature because we're interested in thermal stuff in equilibrium. And so this is our model. We have an abelian gauge field, a Higgs field, which is a complex scalar with its potential, and in principle a gauge fixing as well. Our potential looks like minus mu squared phi star phi plus lambda phi star phi squared, and our gauge fixing looks like 1 over 2 psi d mu a mu squared plus d mu c bar d mu c. And we're going to take the limit psi goes to 0 from above, which is the Landau gauge. Note also that in the abelian theory, the ghosts decouple, so we won't care about them. So when we analyze this at 0 temperature in perturbation theory, normally we draw the potential in terms of some background expectation value phi bar, and it looks something like this. There's a minimum at minus, or sorry, rather at plus mu squared and lambda. And this is kind of the picture of how we understand Higgsing at 0 temperature. At non-zero temperature, we need to include the effect of thermal fluctuations or of entropy. And so we instead consider the effective potential. And were you defined an effective potential already in your thermal field theory lectures? No? Okay. So, in finite volume, which is where I'm going to define things, in finite volume, you have a fixed number of modes. There's one special mode, which is the zero mode, isolated from the first excited mode. So we can isolate the P is zero mode, which is the one I've called phi bar. And if we consider the expectation value of this P equals zero mode in our model, so we're going to integrate over all fields. The ghosts decouple, so we can drop them. Then we want phi bar, which is this P equals zero mode, e to the minus the action. And we're going to isolate the P equals zero mode, integrate over all the non-zero modes, and call the resulting quantity. I guess I should have had a 1 over z. I could have put it in my measure, but I didn't. And we're going to call the resulting quantity our effective potential. So this is a definition of our effective potential. This is the spatial volume. And beta is 1 over the temperature. And furthermore, we can write this as an integral over phi bar times a probability density. Which tells us that the probability density is equal to 1 over z times e to the minus beta volume effective potential. Let's have that one in a square. Oops. So this is somehow the point of this effective potential thing. It tells you how probable different phi values are, phi bar values, where phi bar is the average field in a large volume. So if the effective potential is very large and positive, then this is extremely improbable to have such a value, and if it's large and negative, then it's extremely probable to have that value. Now, we want something interesting to happen. We want maybe phi bar to change value, like in a phase transition. And for that to happen, this effective potential, it can't be the same at all temperatures. It has to change significantly as the temperature changes. So if we write our effective potential as our tree-level potential plus loops, thermal fluctuations always come in loops because they're fluctuations. So for something interesting to happen, the loops bit divided by the tree bit can't be too small. So this, if you do a calculation, loops divided by trees, it always takes the form couplings times loop integrals, or sum integrals, and if we want to work in perturbation theory, then these are assumed small. And for the loops to have some significant effect to change the shape of the potential in general, this has got to be, apologies for going off the end here, bigger than about 1, roughly speaking. The loops have to be bigger than about 1 times the tree level bit. Otherwise, the tree level bit and the loop corrected bit will look the same. This should look different. And given that the couplings are assumed small, that means the loop sum integrals must be big. And loop sum integrals, these are just couplings. There are no couplings inside loop sum integrals. These are only functions of T, the temperature, and masses. That's all they're functions of. And for them to be big, the only real way you can do it is to have a hierarchy of scales. And for that, we're going to need resummations. So I changed color randomly. Oh, well, I'll continue here. And the way to do that is effective field theory. If it's not perturbative, then you don't need a scale hierarchy. But yeah, you need to do something with your non-perturbative model then. If you have some other way to compute, then yeah, that's fine, absolutely fine. So something needs to be big, either the couplings or the loop sum integrals or both. Otherwise, you won't get a big correction to your potential. Yeah, the only other way out is your potential is at 0 temperature, your tree level potential is extremely close to a phase transition already. Then only a small change is needed to have a phase transition. That's another way out. But if your potential at 0 temperature isn't close to a phase transition and you have weak couplings, then you need a scale hierarchy. In the sum integrals? Yes. Sorry, yes, repeating the question. So the first question was, what if we have strong coupling? And the answer is, you don't need a scale hierarchy if you have strong coupling. The second question was, are you integrating over momenta here? I'm integrating over, sorry, I should have continued to write P not equal to 0 on these here. Oh yeah, just on that place. Here I'm integrating over fields. And I'm splitting up the field into Fourier modes, and I'm integrating over all the modes which have a non-zero momentum, and leaving the one with 0 momentum. This will give me the 1PI diagrams, because the reducible diagrams always have 0 momentum going along them. It's another way of defining the effective potential than this Legendre transform trick, for which you don't need convexity. This is defined even if you don't have convexity. It just means you're just splitting up your modes. Yeah.
So
Ah. Yes, I didn't make a mistake. Apologies. It's phi bar, and phi bar is defined as the one with zero momentum. Yeah, it was all good. Apologies. Okay. So I'm now going to introduce effective field theory in the context of finite temperature. Actually, let's go with high temperature. Temperature. Dimensional reduction. So, in finite temperature, in the imaginary time formalism, our fields are a function of tau, which is this imaginary time which goes from 0 to beta, and x, which lives in 3 space. And because they have to have certain periodic or antiperiodic boundary conditions as tau goes from 0 to beta, we can write them as a Fourier sum of purely spatial modes multiplied by ETI omega n tau. Let's write it below. Where omega n is n pi t, and n is odd for fermions, and even for bosons. And as I tried to motivate earlier, we're going to need to consider hierarchies of scale. And in the case of a thermal phase transition where the loops, the things are dominated by T, the thermal scale, or rather pi T, the natural thing to consider is that this is some high scale compared to some other scale. So if we have pi T much larger than some mass, then we have a hierarchy of scales. And as a consequence, something interesting can happen for our effective potential. And we want to look at phi bar and the dynamics of phi bar. And this thing is zero momentum, so it's at very low energies. So we want to integrate out higher energies and make an EFT. So there's an EFT, an effective field theory, for modes with energies much, much less than pi t. And what can live in that EFT? The only things that can live in this EFT are the modes where n equals 0 here. So these are the spatial modes with no tau dependence, and as a consequence they have to be bosons, because fermions always have n non-zero. So the EFT consists of the purely spatial bosonic modes. Now for our abelian-Higgs model, we want to write down as our EFT, our abelian-Higgs model contains the scalar and the gauge fields. So the scalar is somewhat simple, but let me just highlight something with the gauge fields. If we're considering just the purely spatial modes, that means they don't depend on tau at all, then our A mu field, which can be written as A0 AI, under a gauge transformation, A0 would go to A0 plus a time derivative of some gauge function, but we're not including time dependence here, because this is purely spatial theory. So A0 goes to A0, and AI goes to AI plus a spatial derivative of some gauge function. Which means this thing is a scalar, and this thing is a vector. Maybe it's not surprising that when we decompose things in terms of time and space, we end up with our 4 vector being a scalar and a vector. That's what happens. Once we have this, we want to write down for our effective theory the most general model. This is a 3D model because it only depends on spatial directions, because we only have the n equals 0 modes. The most general 3D model which satisfies the symmetries, basically, and has the same degrees of freedom. So we have our AI field from before, we have the A0 field, and we have phi, the scalar. Those are our 3 degrees of freedom. We want to write down the most general 3D model we can. It's again a Euclidean signature because it's just the spatial modes. And we find we of course have the spatial part of the gauge field kinetic term. We have a kinetic term for our new spatial degree of freedom. We have a kinetic term for our scalar, purely spatial. And we have a potential which can now depend on our 2 fields, phi and A0, and then we have gauge fixing. And the gauge fixing, okay, whatever, I'll write it all. What options do I have for my potential? So I have the same symmetries as before for phi. A0 is a real scalar field, and as it only turns up quadratically in the original action, it has a Z2 symmetry, which means I can write down only terms satisfying those symmetries. So there's the same term as before, which is the mass term. I'm here just giving it with a positive sign because I, in general, don't know the sign of this thing. I'm going to put subscript 3 as well to mean the 3D parameter for the 3D effective theory. We have, again, a 3D 4-point coupling. Now that I have a scalar, A0, it can in principle have a mass. Oops, sorry. It's a real scalar, hence the half. I can have couplings between my new scalar and my old one. And in principle, I can also have a self-coupling for the scalar. And for completeness, here's a gauge fixing term. And again, the ghosts decouple because it's abelian. So that's our effective theory. I just wrote down the most general theory I could with the degrees of freedom I had, which satisfied the symmetries. What we now have as unknowns in the theory are the parameters, M3, lambda 3, MD, H3, lambda A, and also there's a G3 inside there. Currently, they're unknown parameters. In order to do effective field theory in general, one matches the parameters, and then you have the theory. And I have 1, 2, 3, 4, 5, 6. Okay, quite a lot of parameters in this model. I have 6 parameters to match. But once I've matched 6 parameters, this model will match all observables into IR. So I match 6 things, a finite number of things, and then I get an infinite number of things for free. So match parameters. Gives all IR observables. Okay. Any questions at this point? Yeah. Pardon? The ghost switch decouple. I just introduced it for completeness because I want to do calculations with this model, so I wanted to kind of show you that we can do something. But otherwise, let's have a 5-minute break there.
Take a break. Stretch.
Yeah, can I ask you a question first?
Sure.
How much of this did you already do?
We resume.
So we want to match those parameters that I just rubbed off. I'm going to give you a little bit of, we're going to need a little bit of general effective field theory stuff. So I'll talk about that. So when we're trying to calculate those parameters of our effective theory, what we do is we match. Oh, someone pointed out that I might have had I had a 1/2 f mu nu squared. It should have been 1/4. Yeah, apologies about that. But okay. When we're calculating those 3D parameters, we match IR observables. And by IR observables, I mean, in a quantum field theory context, correlators with IR or low momentum legs. And we match them between the full theory and the EFT. So pictorially, I'm going to need colors. Okay, infrared is red, and IR is, let's do yellow, why not? So I'm interested in some correlation function. Let's pick a specific correlation function, which has 5 infrared legs. In principle, anything can happen in the middle. And because I've chosen red here, this diagram represents IR on the inside. And of course, I'm only interested in the case where we have IR legs, because these are infrared observables. But I can also have IR legs with UV inside, or IR legs, or the same observable rather, with mixed IR UV inside. In general, these are the 3 options, right? Can't have anything else. And this is the calculation in the full theory where I have all of the modes. In the effective theory, I only have these diagrams with infrared modes. Except I don't have to choose the same parameters. I can choose different parameters in the effective theory, and hence have different looking legs and different looking inside bits. And I can have in potentially new terms like that, mass squared for the A naught field. So this is a resummed IR legs and resummed IR inside. Now, it's maybe not at all obvious that this is in general possible, that I can write an equality like this. It happens to be that it is possible, and this is a special feature of quantum field theory, essentially. Essentially, we have the Appelquist-Carazzone theorem, and this theorem tells us that there exists a choice of parameters over here such that this holds, this equality holds up to corrections which are power suppressed in the UV scale. So, and the theorem is not just down at tree level or one loop, the theorem is for all diagrams. So I can do this at one loop order, I can match everything at one loop order, and I find that I can make this equality hold by choosing the parameters appropriately up to power suppressed corrections. And then I can repeat the process at higher loop orders, and each time I can use this theorem to say that the missing terms, the difference between the left-hand side and the right-hand side, is power suppressed again. So essentially states that there exists a choice of parameters. Where this is possible. The original theorem was somehow specific to certain renormalization schemes, but has been generalized since. Yeah.
So I was wondering if it's a question about the 2D Lagrangian you wrote before.
Yeah.
Shouldn't we, in principle, also choose a different normalization, canonical normalization constant?
Thanks. Yes, in principle, I guess we'll get onto that. When I wrote my 3D fields, you should just think of them as different fields. I used the same letter, but think of them as defined differently. They're defined on the 3D side, and then on the 4D side, in principle, they can have different normalizations. Yeah, I used the same letter. I apologize, that was not clear. This theorem only applies to certain subsets of diagrams, not to all diagrams. It applies to one light particle irreducible diagrams. These are diagrams that are irreducible in terms of the light particles, but maybe reducible in terms of the heavy particles. Fortunately, this set of diagrams is sufficient to generate all diagrams in the infrared theory. So this, in practice, well, it does apply to all possible observables which are purely infrared. So when we're matching, so I will write this as one light particle reducible. As a consequence, we should match one light particle irreducible correlators. If you don't match this set, you don't get factorization of the UV and the IR. But you can always just choose to match these. And then some other sort of general points to simplify matching. when we match, the infrared parts, so basically this diagram and this diagram, essentially cancel. So all that matters in the matching are these ones, really. And really, we only need to match essentially the UV parts of diagrams. So to simplify matching, we project out IR parts of diagrams. And if we're using dimensional regularization, this amounts to Taylor expansion. In integrands. Oops. Is that okay? Oops. Let me give you a reference for this, because this is a bigger topic than I have time to cover. Clifford Burgess, Introduction to Effective Field Theory, covers this topic in some depth. But as an example, if we had the following loop integral where m is much smaller than t, so this thing is IR, and this thing is UV, and we want to project out the IR parts, or essentially just take the UV parts of this loop integral. That means we Taylor expand in the integrand. Well, let's make that squared, just because. And then we'd have 1 minus 2 m squared on q squared plus dot dot dot. Into leading order, we just get 1 on q to the 4. So this is what I mean by projecting out the IR part. So this is a loop integral which contains IR and UV scales. If we Taylor expand in the integrand, order by order, we just get the UV scales in the integral. And the IR scales kind of come out. Now in our matching, we're going to do everything at leading order, in which case we only care about loop integrals which give us positive powers of pi t. So these are going to be the enhanced diagrams enhanced by loop integrals which are large because we have positive powers of pi t. So if I write 1 over q squared to the a here, there's only one scale in this integral, and it's pi t. And if I use dimensional regularization, that one scale is the only scale which can turn up in the answer, which means this must be pi t to some power. Now we have 4 powers of momentum on the top, and we have 2a on the bottom. So this is 4 minus 2a. And if I only care about the integrals which are going to give me positive powers of this energy, and so enhanced stuff, I only care about integrals where a is 1. Yeah. Okay. So the next plan is to actually go to our Lagrangian and do a calculation. Let's match one of these parameters. Let's match the one which is most important for the phase diagram, which is the Higgs mass. In 3D. So going back to this, that means I have two external legs, both of which are Higgs external legs, and I match them in the the diagrams, which is equivalent to matching, and I want to match the 1pi or one light particle irreducible diagrams. So I can define this gamma, which is usually used as the letter for 1pi correlation functions, and I'm going to put the number of fields up here. And let's choose p mu equals 0, because that's all that I will need for the Higgs mass. The Higgs mass doesn't really depend on external momenta. And then I'm going to equate that to the same thing in my EFT, where my 3 momentum is 0. And this should give us, hopefully, the Higgs mass. So the 1pi correlation functions are minus the sum of 1pi diagrams in Euclidean signature. So let's have a look at gamma phi phi EFT first. Serial momentum. So this is the sum of the diagrams. So we get minus m3 squared, which comes from this diagram, plus, what diagrams can I write down? Let's use double lines to highlight that. These are resummed lines. Then I have a Higgs loop. The Higgs couples to the gauge field. I can have a gauge loop. And then I can have the different shape of loop. And what I care about is the UV part of these diagrams. This is all I can get up to this order. And naively, one might think that there's no UV part to these diagrams because I've drawn this in the EFT. These are my EFT diagrams, so there should be no UV part. That actually is correct, as we'll see. Let's just write down quickly the Feynman rule so that we can proceed and do problems. How long do I have? Not very long. I'll do this for the full theory, but it's basically the same for the effective theory. In Euclidean signature, the thing that goes in the exponent is e to the minus s. So the Feynman rules are derived from minus s. Let's do this Feynman rule. You can calculate Feynman rules by taking functional derivatives. In this case, we get minus 2 g squared delta mu nu times an overall momentum conserving delta function. And then we strip this off when defining the Feynman rule, which means that this diagram, where the lines give you phi and phi star. Oh, sorry, this is a star. Here is minus 2g squared delta mu nu. This one is minus 4 lambda, where the 4 comes from, this derivative. And then this one is minus g. Here's a mu, it's p1, it's p2, then we're meant to follow the arrows. And then we have the contractions. Phi with phi star gives 1 over p squared plus m squared, where m is actually minus mu squared. And then a mu with a nu gives 1 over p squared delta mu nu minus p nu on p squared. Okay. In the gauge we've chosen, just sort of thought I'd write that so we're all on the same page in terms of doing calculations. So, now let's consider this diagram, the first one here, the UV part of it. So there are arrows, that's what I should have done, arrows everywhere. There's only one way of closing this loop, so the symmetry factor is 1, so we get minus 4 lambda integral over q of 1 on q squared plus m squared. And we only care about the UV part of this diagram. To get the UV part, we Taylor expand under the integrand. So we get 1 on q squared, 1 minus m squared on q squared, plus m to the 4 on q to the 4, plus whatever. And now, because we're using dimensional regularization, and all of these integrals are pure powers of q, these all 0. Same is true for any of these. Once we power expand in q, then there are no scales. So all loop integrals are 0. Which tells us that gamma EFT phi phi is m3 squared. And that's it. Sorry, the UV part. And we only need to match the UV parts. Running out of time, aren't I? Now, in the full theory, if I match the same thing, it's the sum of diagrams. We get mu squared plus and we want the UV part. And because we want the UV part, I can just not write down any m squareds anywhere, because I'm going to project that out by power expanding. So I'm just going to drop m squared everywhere in the integrand. So this one, symmetry factor is 1. 4 lambda is the vertex. And we have 1 on q squared. This one, there's 2 ways of joining this because there's no arrow. Symmetry factor is 2. Vertex gives me delta mu nu. And then the propagator gives me q squared delta mu nu minus mu, q nu. That's this diagram. And the last one symmetry factor is 1. If I cut that, there's only one way of rejoining the lines. And this momentum is 0. This is non-zero, so we only get one of the two momenta in the Feynman rule. Only one of these two turns up. So we get q mu, q nu on q squared, q to the 4, delta mu nu minus q mu on q squared. Yeah. Yeah. Okay, so I went too low. So with this diagram, maybe you can spot it's 0. If I contract q mu q nu there, I get q squared. And if I contract q mu q mu there, I get q to the 4 on q squared. So this diagram gives 0. So the remainder of the diagrams, I get mu squared minus 4 lambda, and then this sum integral is t squared on 12, and then I have this diagram here. You can contract the indices. Delta mu nu is going to give you a factor of 4. Delta mu nu on, oops, they should be dimensionless. On q mu nu on q squared is going to give us a factor of -1 here. So we're going to get 4 minus 1, or 3. This is just a projector onto 3 once we do this here. So then we get -2 times, we had a symmetry factor, didn't we? Minus g squared times t squared on 12, all times 3. And now if I match these two, if I demand that I will find m3 squared is minus this lot. Lambda on 3 plus g squared on 4 t squared. And this thing, if I take, now I have the Higgs mass, the effective Higgs mass in this theory. If I take t to be 0 or t to be small, then the first term wins, and it's negative. So it's negative for small temperatures. But if I take t to be sufficiently large towards infinity, then this term will always win. And so we'll have this is positive for high temperatures. So we have a mass which is changing sign now in our EFT. I think I'm roughly out of time. 8 minutes? Okay. So we got that power enhancement that I mentioned before. The UV scale enhances the loop contribution. This is the loop contribution. This is a tree-level contribution. So tree-level plus loops, they can be the same size, when T is big enough. When we have a hierarchy of scales, T is bigger than mu. As well as masses, I had couplings. What if I were to match the coupling? So I argued before that the only loop integrals which are going to give me positive powers of temperature are 1 over q squared type loop integrals. We had 1 over q squared in all of these cases, essentially. If I were to look at corrections to couplings, so this diagram plus this diagram plus this one, I always have more than one propagator. I can never just get one propagator in there. So I'm always going to have more powers of q on the bottom. You can work it out and see, okay, there's some q's from the vertices in this case, but overall we get even more propagators. In this case we have 4 propagators, so even though I get 4 q's on the top, I get 8 q's on the bottom. So overall this is not going to give me 1 over q squared, and neither is this. In fact, if you work it out, this one is, okay, this one's like lambda, this one's like lambda squared, 1 on q to the 4, and let's just work out this one over here. This one, why not? This one's like g to the 4. I get 4 q's on top, so 4 on top, but I have 8 on the bottom. So it's again 1 on q to the 4. So none of these are power enhanced. So at leading order, we can drop loop corrections. To couplings. That is, I just take this diagram. One thing I'd like to point out, which was highlighted in a question, mass dimensions are different in different spatial dimensions, or space-time dimensions. So canonical normalization, we kind of need to do calculations or to understand what we mean by a field to some extent. But canonical normalization is different in 3D and 4D. And we can see this by, in 4D, I would get something like this. Where I have my integral from 0 to beta. But in 3D, if I want the thing to be normalized the same way, I don't have a beta, because there's no time integral. Which means that my 3D field is related to my 4D field by 1 on square root of temperature. That's because here we have 1 over temperature, and here we have phi squared, basically. So phi squared 3D is like phi squared 4D divided by temperature. So let's take stock a little bit. What have we achieved in doing these calculations? We now have, let's imagine we've computed the others. We would then have an effective field theory with a potential which depends on phi bar and a naught bar. These are the background values, which looks like half m3 squared plus quarter lambda 3 phi bar squared plus phi bar to the 4 plus half md squared 8 naught squared plus, I won't write the rest. So we're here. Phi is basically phi background on root 2 plus fluctuations. That's where the 2 comes from. And we now know, if we've done this calculation, what these parameters are. From this canonical normalization story, we get that lambda 3 is actually lambda times t, working out the factors of t that come from canonical normalization. And this one we worked out before. If we just focus on the phi direction, we get the following picture. That at sufficiently high temperatures, we have a potential which looks like this, because this is positive. At sufficiently low temperatures, we have a potential that looks like that, because that is negative, m3 squared is negative, and in between it's 0. And we can work out the temperature at which that happens. m3 squared equals 0 implies that T squared, I'll call it the critical temperature, is equal to mu squared on lambda on 3 plus G squared on 4. So in terms of the story at the beginning, in terms of the phase diagram, we've worked out something. We've worked out that at high temperatures, we're in a symmetric phase. At low temperatures, we're in a broken phase in the usual story. And there's some critical temperature in between. This is a second order phase transition. Yeah, we'll look at that more in the exercises. And what would happen if we were to calculate higher order corrections? If we were to calculate all of these things, all of these corrections to these parameters, all that would happen is that these parameters would change as functions of temperature. They'd become more complicated functions of temperature in general. But the form of the effective potential from the 3D perspective looks the same. It's always the same, the parameters will change as a function of temperature. So if I have the parameters m3 squared and lambda 3, lambda 3 grows with temperature, m3 grows with temperature, it looks something like this. So a given 4D model will give you a line in this parameter space. Yeah, something like that. And if I change my 4D model, or if I change the accuracy of my calculations, I get a different line. Different 4D models, different accuracies will give me different lines. But in terms of the 3D parameters, everything's the same. So that's a kind of universality we have. And that is it. Thanks.
Any questions?
So, thank you for the lecture. What I meant before by the normalization constant, I didn't mean the dimensions of the field, but the actual, say, the parameter that goes with the kinetic term of the scalar. Should you include that, or like in principle when you build your EFT Lagrangian, or is there a way to do this matching so without this term?
Yeah, there's two ways to do it. One is to say, would be an unconventional way to do things, would be don't include it, and say that phi 3D and phi 4D are the same field, essentially, in the IR, but then your 3D field will not be canonically normalized. The other way would be to canonically normalize the two theories, and then, as well as this T, you will get corrections, but those corrections are suppressed by couplings, which is why I didn't do it at leading order here. But in principle, there is a matching relation for this, which is basically because you want them both to be canonically normalized, and those are independent constraints. So, yeah, you then have to relate the two.
Other questions? Okay, otherwise, I think we can also take now the coffee break for asking more questions again. Thank you so much.